Hi, welcome back. Today we're going to be taking a look at acceleration and velocity problems. You might recall last year in BC in calculus that we talked a lot about velocity and speed. We said if we let velocity of a function be r prime of t, remember this is the derivative of our position graph, we can get speed by taking the magnitude of that. The acceleration vector, again just like in BC from last year, the acceleration vector will be the derivative of the velocity vector, both of which you notice are vectors as well. So acceleration is our derivative of velocity, or our second derivative of our position or our path. Now, oftentimes we are going to need to write acceleration of a particle in terms of its tangential and normal components. If we do this, we can describe acceleration as the following. Acceleration is our tangential component of acceleration. Now we're going to take a look at kind of an image of this later on. Tangential component, and we can write this in terms of our normal component. Now I'm going to have a proof in another video to kind of go over how we get both of these. But a quick way to kind of look at it is if we have a particle moving along this path, at any given point, we of course have our tangential portion, the direction of the tangential, and the direction of our normal. Oops, not a vector, sorry. Now, to get the acceleration of our tangential component, AT, that is just the acceleration times our tangential unit tangent. And again, I'm going to show this in a proof in just a few moments, okay? So, in another video. Acceleration, we know, is our second derivative, r double prime of t. And we know from another video or another lesson is that our tangent component is r prime of t over its magnitude, r prime of t. And we can kind of shortcut that by writing this as this r double prime of t dot with r prime of t over the magnitude of r prime of t. To get the normal part, this is a little bit trickier to do. To get the normal part, we know this is perpendicular, so I'm going to do take the acceleration component, the acceleration, times the normal component. So this becomes, and again I'm going to prove this in another video, the magnitude of r prime crossed with r double prime of t over the magnitude of r prime. And again, we're going to talk about how we can prove these graphically in another video right there. For now, we're just going to kind of memorize those videos. Alright, so vectors t and n, remember from another video, are unit vectors, and the normal are the unit tangent and the unit normal component of the position vector. If we define the magnitude of v as the norm of the velocity vector, then of course we can get our two equations. We get our tangential component for acceleration and our normal component of acceleration. Now, if you notice, to get the normal component of acceleration, we have this kappa v squared. And we should remember that this is basically saying v squared from our curvature is that this is now v squared over r. Remember, kappa was 1 over r. And this, remember, should sound familiar to us. This is that centripetal acceleration. So the normal component of acceleration, it gives us our centripetal acceleration from physics. Alright, so we'll talk about these in another video, how we get those, but for now let's just look at a few examples. We want to find the velocity and acceleration vectors at t equals 1 given this position vector, r of t equals ti plus t cubed k plus 3tk. So I want to find my velocity vector first, so let's go ahead and do that. Our velocity vector, which is r prime of t, becomes, and I'm going to write this in chevron form, 1, 3t squared, comma 3. To get v of 1, we get 1, 3, 3. So there is our velocity vector. To get the acceleration vector, this is the second derivative of r. And this becomes, 0, 6t, 0. And then to find the acceleration vector at 1, we're going to get 0, 6, 0. Right. Now, the next question says, find the tangential and normal component of acceleration vector. So now, remember, what we're talking about right here, if this is my vector right here, if this is the path of my acceleration, I want the tangential component of it, and I want the normal component of that. So to get the tangential component, we are going to use our dot product, r prime dot r double prime over the magnitude. So our tangential component is given by r prime dot r double prime over the magnitude, r prime, times t of t, right? Remember, this t of t, that is our unit tangent. But let's just go ahead and get the component right here, r prime, r double prime. So I'm going to dot those. Well, I already got those. Here's r prime, there's r double prime. So I can do that quickly in my head. Now remember, this is a scalar, so that becomes 0 plus, what's that, 18t cubed plus 0 over the magnitude of 18t, over the magnitude of r prime. So let's go ahead and get that. That becomes 1 plus 9t to the fourth plus 9. And of course, we're going to get 18t cubed over the square root of 10 plus 9t to the fourth t, whatever your unit tangent is. To get the normal part, remember this one is the cross product, r prime cross r double prime, over the magnitude of r prime t. There we go. So I have to find the cross product of r prime and r double prime. So we're going to do that. I, j, k, 1, 3t squared, 3, 0, 6t, 0. And if we do this, what we wind up with is, let's see here, we're going to wind up with negative 18t. I'll put these in chevron form. The j's, we get 0j, so 0. And then the k's, we're just going to get, what's that, 6t? So 6tk. The magnitude of this is the square root of, now 18 squared is 324 t squared plus 36t squared. And if we write out our unit, our a sub n, it's going to become the square root of 360 t squared over the magnitude of r prime, which we already got before. That's root 10 plus 9t to the fourth, n. Now, so the n, remember this is just our unit normal, right there. All right. So there we have part one. Go to part two. We'll take a look at a few more examples. Hope you guys enjoyed this one. I'll see you then. Bye-bye.